Today we are going to discuss collision theory. This was developed by Arrhenius and Wontov. There is another theory called absolute reaction rate theory. According to collision theory, collisions are essential. If each collision leads to formation of product, all gaseous state reactions are expected to be explosive and fast, but that is not really happening. That clearly indicates that all collisions are not said to be fruitful collisions. The fruitful collisions are those which lead to formation of products. Means once reacting molecules acquire certain sufficient amount of energy, minimum amount of energy, they can only participate in the reaction. So that is one is collisions. Second thing is sufficient energy. These two are essential things for formation of products. According to this, rate is said to be product of collision frequency and fraction of reacting species are in activated state. This is the Z, this is the Q. Z can be estimated from the kinetic gas theory. If these two are the molecules which are going to come and collide, this is the radius of say A, this is the radius of B, and here collision pair may sweep and resulting a cylinder volume of this. This is the collision diameter. This in fact is the RA plus RB is the collision diameter. So the volume of cylinder which is resulted while sweeping this pair in a given direction is the pi r square h. R square h can be written as d square. H is the height, which is written as this average velocity of the molecule. So that is average velocity in unit time. Units in unit time are second, 1 second. So this volume can be written as pi d square nu bar. The number of total number of collisions in 1 cc in 1 second can be written as pi d square Na, number of molecules of A, number of molecules of B. This is the Z pi d square C bar Na and B. This can be written as sigma may be described as collision cross section. see average velocity from the gaseous state. What we can take 8 kT pi mu, where K is the Boltzmann's constant, T is the absolute temperature, Kelvin temperature, mu is the reduced mass, mu of the pair can be taken as M, MB, MA plus MB. Now Z can be written as pi d square 8 kT pi mu under root NA NB. Now Q is the fraction of molecules which are in activated state. This is the ratio of the molecules which are activated state to the total number of molecules present in the system. This can be expressed in terms of minus exponential minus EA by RT. This is the Boltzmann's distribution. Boltzmann's distribution. Now the rate can be expressed as Z into Q is the pi d square 8 kT pi mu NA into NB minus EA by RT. This is the rate equation. Rate, as you know, is a K2, in fact NA and B, since it is the bimolecular collision. Bimolecular collision. Now, therefore, rate this can be expressed as the pi d square 8 kT pi mu the root minus EA by RT. This is the rate constant equation. Theoretically, we can estimate. So this pi can be this collision diameter d, collision diameter can be readily calculated using molecular diameter derived from the viscosity data. D square is equal to 2 eta 3 pi n RT by pi m, where this is the density term. Density, this is the viscosity of the gas. There's density of the gas, where N is the number of molecules per cc, and activation energy can be estimated from the experimental variation of rate constant K2 with temperature. ln K 1 upon T, negative slope negative EA by R. EA can be calculated from slope which is into R. Now the question is successful nature of this collision theory. If it is applied to the reaction like decomposition of H2 plus I2 at 556 Kelvin, K calculated is 5.2 into 10 power 7 liter per mole per second. Experimental value was found to be 3.5 into 10 power 7. A good agreement with the experiment. But many cases the K value is completely, K observed value is different from K calculated value. While comparing with the Arrhenius equation, as you know, K is equal to A minus EA by RT. When there is a discrepancy between observed and calculated, this is the, say, observed from which, and K calculated from the earlier equation, then to estimate the actual value of the K, a probability factor was introduced. RT. Probability factor is said to be, or this is also called steric factor. Steric factor. This P is K observed by K calculated. Here the various attempts were made to correlate the values of steric factor. One is the orientation factor. Say orientation factor is required to form transition state. Orientation effect will cause a low value of P to be observed. For example, this is BrNO2 OH minus. Reaction is this. OH minus can approach from this end and this end, but proper orientation is required for the product formation. Hence, such type of reaction probability factor is less. In many cases, the probability factor or the steric factor varies, is less than 1. Now we can compare PZ is A, P is equal to A by Z. The steric requirement can also be explained due to disagreement between experiment and theory by replacing sigma in earlier equation by react to cross section. This can be viewed in this manner. Say earlier we discussed with the collision pair. This is said to be the sigma. The collision cross section. This is the collision cross section. Collision cross section. This is said to be the sigma star. This is the reactive cross section. If the reactant molecules move in this direction, deflection takes place. The deflected molecules will not lead to form the products. If they come in this direction, that results the products. The sigma star can be regarded as the target area for the reaction, whereas sigma itself is the target area of a reaction of non-reactive collision. Sometimes it is convenient to express sigma star as a multiple of sigma by introducing steric factor P and writing sigma star as P sigma. Then rate of reaction. Now we can introduce the P to get the experimental value. This into N E/RT. Some cases the probability factor, very few cases, very more than 1, 4.8. This is an example K plus Br2, KBr plus Br. In this reaction, the distance of approach at which reaction occurs appears to be considerably larger than the distance needed for deflection. This can be explained on the basis of harpoon mechanism. When potassium approaches Br2, say temporary dipoles are resulted, positive, negative. So that harpoon, that electron density, which is expressed in terms of a sphere, say harpoon mechanism, which extends the cross section for the reaction encounter. Reaction rate is underestimated by taking for the collision cross section the value for simple